Well, hello and welcome back. Hope you're all keeping safe, and thanks a lot for encouraging these videos all along. Um, so, in the previous videos, we have talked about simple parametric evaluation of a couple of analytic and non-analytical functions, particularly like z and z bar. We've worked with circular and square contours. Um, in this particular video, I just want to introduce what's perhaps one of the most important integrals in the study of complex analysis, which is the integral of the function wz equals 1 over z. So we look at the function wz equals 1 over z. And as before, let's just try to evaluate the integral of this function parametrically along a circle of radius r centered at the origin, for instance. So let's just see what comes out of it, and then we'll carry on the discussion from there. So the contour, as a contour, let's choose a circle of radius r centered around the origin. And as before, we'll use, I'll put a link to the video where we have worked out other integrals using the circular contour. But along this particular contour, the complex number z can be written in polar form as r e to the power of I theta. And as you move along the contour, the radius doesn't change, it's only theta which changes. So the differential of this essentially is I r e to the power of I theta d theta. So if you are to evaluate this integral, let's say we are moving along the contour once in the counterclockwise direction, and we evaluate the integral of 1 over z dz along this particular contour. This just comes out to be, so if you put in z equals r e to the power of I theta, we'll have 1 over r e to the power of I theta times dz, which is I r e to the power of I theta d theta. And there's a lot of simplification that happens here. So the r just cancels out, e to the power of I theta cancels out, and all we're left with is I times d theta. And as you move along the circle once, theta essentially goes from 0 to 2 pi. So if you evaluate this integral, essentially the integral is I times d theta from 0 to 2 pi, and what we end up getting is 2 pi times I. Now this is a particularly interesting result for two main reasons. One, you can see that this is non-zero, so it's not 0. Right? And if you recall some of our discussion on integrals of analytical functions along closed contours, we know that from Cauchy's theorem that the integral should evaluate to 0. So this integral is non-zero. Now you could say that, well, maybe the function is non-analytic. Now we've also looked at one non-analytic function, which is the integral of z bar along a contour, and what we found was that the integral was I times 2i times, I think, the area enclosed under the contour. But in this particular case, it seems that the integral also does not depend upon the choice of the contour. So perhaps this integral does not, or rather I should say, it does not necessarily depend upon the choice of the contour. Depend upon contour. And the reason I say it does not necessarily depend upon the choice of the contour is because it's still 2 pi times I, and you could say that, okay, maybe the 2 pi is coming because of the circle. And the reason I feel that it perhaps does not depend upon the choice of the contour is because it does not carry any signature of, let's say, the radius of the circle. So we can sort of explore this fact a little bit further by, and instead of looking at a circular contour, we can now look at a square contour and form this integral and see what comes out of it. So let's try that. So I won't go through all the steps, and I invite you to try this as a short exercise just to see what you get, and feel free to write to me or discuss this in case of any problems. But the essential idea is, let's try and integrate this function along the square contour. I'll just lay out the steps for you here. And I'll also put a link to the video where we've talked about how to work with square contours before, so I'll put a link to that as well. So as an example, what we can imagine is a contour of this kind. A square contour centered around the origin, and you move along this contour once, and let's say this goes from x equals minus 1 to 1, y equals minus 1 to 1. Now you can break this contour down into 4 segments. So let's say this is segment 1. So So you move along A to B, then you move from B to C, then you move from C to D, and then you move from D to A. And you want to integrate this function along each of these segments, and the entire integral along the integral along the entire contour is the integral along AB plus the integral along the segment BC plus CD plus DA. Now, since we are working with straight line segments, it's more natural to work with the Cartesian representation of the function. So for this particular function, one of the ways of finding out the Cartesian representation is we can take the function W(z), which is 1 over z, and we can multiply and divide by the conjugate of z. So that's z bar. Now if z is x plus iy, then z bar is essentially x minus iy, and z times z bar is modulus of z squared, which is just x squared plus y squared. So this gives us the real part of the function, which is x divided by x squared plus y squared, and the imaginary part, which is minus y divided by x squared plus y squared. And now we need to, and now let's focus on, let's say, one of these parts. So I'll try and perform this particular integral, and then leave the rest as a short exercise. So let's say you would evaluate this integral along the path AB. Now along the path AB, as you can see, the x coordinate is not varying. It's just y, which is changing from -1 to 1. So for instance, the coordinates of the point A are x equals 1 and y equals -1, and the coordinates of the point B are x equals 1, y equals 1. And so the integral along AB is essentially the integral of this function evaluated at x equals 1, so this is z, evaluated at z along AB rather, is this function evaluated with x equals 1. So I just put it in here. So it's 1 minus iy divided by 1 plus y squared. And now we need to figure out what dz is. And again, since x is not varying, if you take the differential of this, we have dx plus I times dy. But x is not varying, so dx is just 0. So this is nothing but I times dy. And as you move along AB, you're essentially going from y equals -1 to y equals 1. So all we need to do is perform this particular integral. We parameterize it now, and now we just need to perform a couple of real integrals. So this integral, you can break it down into two parts. One is coming from this part, which is 1 divided by 1 plus y squared times I times dy. So I just write it in two steps. So one of the integrals is I times dy 1 plus y squared, where y goes from -1 to 1. And the other is coming from this part, which is minus I squared, which is 1. So it's essentially the integral of y times dy, 1 plus y squared, from -1 to 1. Now this integral is easy, essentially because the function here, y divided by 1 plus y squared is odd, and you're integrating from -1 to 1. So this is just evaluated to 0. And you can also do this by substitution. So for instance, you can substitute 1 plus y squared as some variable s, and then perform the integral explicitly and check whether it indeed turns out to be 0. The other integral is the integral of the function 1 divided by 1 plus y squared. And again, this you can perform by making the substitution. So you can make the substitution that y is tangent of theta, and then dy is the derivative of tangent of theta, which is secant square theta d theta. So what will happen is, if you put in this substitution inside the integral, we have secant square theta d theta here times 1 plus y squared, which is 1 plus tangent square theta. But 1 plus tangent square theta is also secant square theta, so the denominator is also secant square theta, and so it just cancels out. And since the value of y is going from -1 to 1, one of the ways we can express this range with the choice with the variable theta is that theta goes from -pi/4 to pi/4. So -pi/4 to pi/4. And when you perform, and when you just substitute in the values, what we end up getting is the integral of d theta from -pi/4 to pi/4. There's also a factor of I here, so I times this, and that's nothing but I times pi/2. Okay. So the integral along the segment AB turns out to be I times pi over 2. Now you can repeat this process for the other 3 segments, and I again invite you to try this out, and you'll see that each of these segments you pick up a factor I times pi over 2, and when you sum them up, the integral evaluates to 2 pi I, just like it was for this circular contour. So this is very interesting, and what we'll do is in the next part of the video, we'll explore the function wz equals 1 over z in a little bit more detail. And essentially, this integral, this particular result, really lies at the heart of many of the beautiful results that come out from the study of complex integrals. So I invite you to really try this exercise out and just think about it in your own time. And hope this will be of some use, and hope to see you soon again. So take care and stay healthy. Thanks for watching.